Let us look at organic carbon aerosol and their climate impact. The organic carbon here are considered as black and brown. Let us look at what are they. Basically, most of the organic aerosols can be characterized as white. That means they efficiently scatter visible radiation. But there is a significant and highly variable fraction of carbonaceous and organic aerosols which absorb actually radiation. So the most important light absorbing carbonaceous aerosols are called as black carbon. Black carbon means basically they are soot-like particulates generated by fossil fuel combustion and biomass burning. Black carbon absorbs solar radiation over a broad spectral range, that means from ultraviolet to infrared region. Most organic carbon compounds absorb IR and UV radiations strongly but are relatively transparent to visible, that is from 400 to 700 nanometers, and near IR from 700 to 2500 nanometer wavelengths. But certain type of organic carbons absorb radiation effectively in the near UV region, that is 300 to 400 nanometer, and in visible ranges. They are called as brown carbon. So we have two different types. One is called the black carbon, another one is the brown carbon. So what are the dynamics played by these two black and brown carbons? Let us look at the both black carbon and brown carbon immersed in cloud droplets absorb light and they facilitate water evaporation and cloud dispersion. So this is an additional indirect effect that counteracts the cooling effect of cloud droplet nucleation by aerosols, because the nucleation in the clouds happens at a very low temperature. We had seen that is around minus 38 degrees centigrade. So that is actually a cooling effect which are produced by the clouds, but they are counteracted by the black and brown carbon if they are present in the cloud. So the black carbon compounds have the lowest volatility and have the strongest light absorption properties. Emissions of primary brown carbon have been attributed to forest fires and biomass burning, residential heating by wood and coal, because Arctic region is extremely cold, so people use firewoods to keep their house warm. Coal and the biogenic release of fungi, plant debris and humic matter are the sources of brown carbon. The brown carbon has two components, a water soluble fraction with the most absorption near UV, and a methanol soluble fraction with a higher absorption due to the presence of large molecules and conjugated aromatic rings attached to the polar functional groups. Here is some of the information related to brown carbon occurrence in the Arctic region and its contribution to climate forcing, mainly the Arctic haze phenomenon. So why it is important to climate forcing? Because the Arctic haze phenomenon occurs because of the presence of brown carbons. They play a key role in the climate forcing, and their optical properties are actually due to low solar elevation angles and also reflective surfaces of airborne and surface ice. So these are all the two major reasons why they are very important. And then they also increase the optical depths. So the radiative effect which happens because of the Arctic haze is light scattering and absorption. So solar lights are being absorbed by the brown carbon aerosols. What are the major sources of the brown carbon? The first one is the boreal fires, and the second one, they are also having the long range transport. That means anthropogenic emission from the mid latitudes also travels to Arctic region. Then what are the radiative and environmental effect? Direct and the indirect atmospheric effects include light absorption by brown carbon. This decreases the surface albedo, and this accelerates snow, ice and ice melting, because in the surface albedo what happens is the solar radiation after hitting the earth, it is again released back to the atmosphere. But if the brown carbon holds those long range radiation, then the heat doesn't escape to the upper atmosphere, they are retained in the atmosphere. So that means that leads to more warming in the Arctic region. That is the reason snow and ice gets melted. Then when we look at the impact on the snow and ice, the melted brine actually modifies the snow photochemistry, This also affects the halogen atom release, because we will be looking at volatile organic compounds, halogen chemistry and ozone chemistry in the later part of the course. So there we will study more about these effects. So this is also leading to ozone layer depletion. So we will study about various reactions that are involved in the later part of the course about these particular effects. And the correlation and the composition is basically how do we know aerosol, the brown carbon present in the aerosol is responsible for that. We can do some mass spectroscopic analysis. So the higher oxidation of brown carbon constituents correlates with enhanced absorption. So this is one of the ways by which we can actually correlate the brown carbon to atmospheric heating. And also the influence of the initial molecular composition of atmospheric oxidation, so aging. So these are some of the chemical reactions that can be used to find out how the brown carbon affects aerosols mechanism. So let us look at the biomass burning and organic aerosols. The aerosol particles from the primary source include mineral dust, sea ice, sea spray, terrestrial primary biological aerosol particles such as fungal spores and pollen, primary organic aerosol such as brown carbon and black carbon. These are formed by the biomass burning, and the entire event is called biomass burning organic aerosols or BBOA. The term atmospheric aging, which we referred in the previous slide, means it is a process that changes the physiochemical properties of aerosol particles during their residence time in the atmosphere. So that means they are getting old, very similar to that. So the residence time in the atmosphere increases because of the presence of brown carbons. This process can take place at the surface of the particle or within the condensed phase. These physiochemical properties mentioned above influence the rate of chemical process during the aging of the aerosol particle, because we know aerosol typically exists for a few days to a week, but when the aging is there, in other words, when brown carbons are present, they prolong the existence of the cloud for longer time. Let us look at some of the chemical modifications of the aerosols. We can have three different questions: what, how and where. So in the first question of what is the chemical modification of aerosols? So this is atmospheric aerosol particles from primary and secondary sources. So they undergo chemical modification. And how do they undergo modification? Bulk and heterogeneous chemical and photochemical reactions are responsible for this particular change. And where they are actually taking place? In the condensed phase and the surrounding gas phase. So this is how we can understand how the chemical modification affects the aerosol. The area to volume ratio of the atmospheric aerosol determines the extent of the surface, that means interfacial one, versus the bulk reactions, because we have two major types of chemical reaction that may be occurring. One is at the surface of that particle, second one in the condensed or the interior phase. That is what we call like a surface reaction or the bulk reaction. This is changing the chemical composition and physical properties of the particles. So this ratio also changes with evaporation and water uptake process due to changes in the temperature and relative humidity. So here are some of the processes that are given, some of the chemical reactions and the processes involved in the atmospheric gas, particle and droplet phases. The gas phase chemistry include volatile organic compounds oxidation and degradation, volatile organic compound oxidation and their formation, nitric acid formation from NOx, sulfuric acid formation from SO2. So these are all the various reactions that occur in the gas phase. And there are also other type of reactions which are occurring. One is called the heterogeneous chemistry. Here gas or the solid or the semi-solid particles are involved in the reaction. Some of the reactions include ozonolysis of organics, oxidation of organics by OH and other reactive OH radical and other reactive oxygen species or reactive nitrogen species. There is also other reactions which are catalyzed on the surface of oligomerization or polymerization reaction. Then when we talk about the interfacial chemistry, so here some of the reactions include dissolution, that means proton, ligand and photo driven reactions are some of the examples. And here complexation of organic and inorganic ligands takes place, and photo generation of reactive oxygen species such as hydrogen peroxide. So all these things happens in the interfacial chemistry, and also there is aqueous and the interfacial chemistry which happens between gas and the liquid one. Here various chemical reactions are given. Hydrogen peroxide reacts with iron 2 species to give OH radical and the OH anion and Fe3 plus. So this is basically called as the Fenton type reaction. So these are all the various reactions that are happening at the aqueous and the interfacial chemistry. In the accompanying e-text, you will get more details about all the individual reactions. So here is a comparison of many of the aerosol types, where they are produced. One is the industrial or urban pollution, another one is formed from the biomass burning, then mineral dust, biogenic and biological origins, marine and the volcanic type. So these are all the several types of aerosols that are present, and how they are emitted, what are their main composition, what is their typical size, what is their hygrospecificity, and absorptions are given in this form of the table. So you will get more details about this table in the accompanying text. We will briefly go through some of the major class. One is the biomass burning. So here mostly the black carbon and the organic ocean acidification, also gaseous precursors of volatile organic carbon, sulfur dioxide, nitrogen dioxide, or the gases which are producing the biomass or the burning smoke. So these main composition is, they are basically carbonaceous materials, that means carbon containing compounds. Their size is typically submicron in the range, and they are hydrophobic at emissions, more hydrophilic after aging. Because when the aging happens, they are actually getting along with lots of water or the water vapor that is present in the cloud. So that is the reason they become more hydrophilic. Their absorption properties are basically moderate, and it depends on the combustion temperature and the fuel type. So when we go to the next important one, which is the marine one, so here we have the primary gaseous precursors, and we will study about dimethyl sulfide reaction and some of the isoprene reactions in the later part. So here what are the main composition of marine aerosol is basically sodium chloride, sulfate, and organic aerosols. Their size is also submicron range, and they have a high hygroscopicity because they are marine. In other words, they have lots of moisture in it, and but their absorption is extremely low.